Now let's see. 4.2 is about bonding and structure. So first we start off with lattice structures. And what they said here, most ionic, metallic and covalent compounds are crystalline lattice. So that means the structures keep repeating. Okay, keeps repeating. So for example, like ionic, right? So we have Na plus. Let's say we have Na plus, followed by Cl, Cl plus, Cl minus, connected to Na plus, and so on. So it connects in all directions, left, right, up, down. So they form a crystalline lattice. And after that, the ions, atoms, or molecules are arranged in a regular and repeating arrangement. Okay, so that is the meaning of lattice. So it is regular and repeating arrangement. So it can be the arrangement of ions as in ionic compounds. It can be in metal is actually ion also is the metallic cation that arrange. So for example, like in metal is like Na plus, Na plus, and Na plus. And then in covalent compounds, let's say for example iodine, so iodine, iodine, and iodine, they arrange in molecules by molecules. Okay, the molecules that repeat. So there will have forces in between. So the forces here is the van der Waals forces. So we go through one by one. We start from giant ionic lattices. So we have an ionic bond in between of the ions. So it's an electrostatic force between a positively charged metal, the cation, and a negatively charged non-metal ions. So that is here, or these are the ionic bonds. So the metal becomes positively charged as it transfers electrons to the non-metals, becomes negatively charged. Okay, so the electron is given to the chloride. Okay, so sodium is giving electron to the chlorine. Now, ionic compounds are arranged in giant ionic lattices, so which is also called giant ionic structures. So that means it just extends in the 3D shapes. And the types of lattice form depends on the sizes of the positive and negative ions, which are arranged in an alternating fashion. So something like this, alternating fashion, positive, negative, and so on. So the ionic lattice of magnesium oxide and sodium chloride are cubic. So they are arranged in cubic. Okay, now let's see the structure. Okay, so you can see like what we said, what we discussed just now, they are in alternate. So sodium is surrounded by chloride, and chloride, and chloride is surrounded by sodium. Okay, so which is what we call the alternates position. So likewise, magnesium oxide is just similar. So magnesium is surrounded by oxide, and oxide is surrounded by magnesium. So they form a cube shape. And after that, this is the the 3D shapes. So you can see we have the green color, the negative ions, which is surrounded by positive ions, and the positive ion is surrounded by negative ion. So which is actually something like this, but when they're all put together, you will see it like this. They are like alternating. Okay, so let's move on. So we have done ionic lattice. Now we look at covalent lattices here. So what we have is, first, it is covalent bonds that is within the covalent molecules. So covalent bonds are bonds between non-metals in which electrons are shared between the atoms. Okay, they share electrons. Covalent compounds can be arranged in simple molecular or giant molecular lattices. Okay, so two situations. Simple molecular, for example, water. Water is simple molecular. Giant molecular lattices, for example, diamond. Diamond is giant molecular lattices. Of course, let's look at simple molecular first. It is molecule by molecule. So the H2O keep repeating, and they are held together by hydrogen bonds. Okay? Hydrogen bonds hold them together. So that is why we call it lattice, where there is a regular arrangement. So this is another example. So this is Buckminster fullerene C60. So it's a simple molecule also. It is 60 carbon that form a molecule. Okay, so it's like a football shape. So you can see.
Wait.
Yeah.
So is the bonding between them, are these like weak intermolecular forces or are they covalent bonds?
For this case, it is intermolecular forces over here. Covalent bond is inside the molecule. For this case, all these are covalent bond. Covalent bond.
Okay.
Yeah, so we have covalent bond for this case. You can see something like covalent bond is within a molecule. So this is one molecule. So covalent bond is within them. And this Buckminster fullerene is considered one molecule. So this whole ball is one molecule. So inside the molecule is covalent bond. Of course, if you have one Buckminster fullerene with another Buckminster fullerene, so in between them, of course, that is the intermolecular forces, which is the van der Waals forces. Okay, so let me label it. So this is covalent. So in case if you have another C60, and then this one is the van der Waals. Okay, now let's see here. This point, simple molecular lattices, we have iodine, Buckminster fullerene, and ice. So iodine, let's say. So iodine, how is it? It's like I2. Okay, it's like I2. So something like this. I2, one molecule. I2, another molecule. And then I2, and then I2. So covalent bond is inside the molecule between I and I. And then this one is the van der Waals forces. Yeah. So then these three are simple molecular lattices. Okay. We still call it lattices because it repeats, the molecule repeats. So this molecule repeats here, this molecule repeats, and repeats. So that's why there are simple molecular lattices. And the next one is giant molecular lattices. So we have silicon 4 oxide. Silicon 4 oxide is basically sand. Example will be sand. And then graphite is made of carbon. Diamond is also made of carbon, but they have different arrangement. So let's look at the details on the next page. Okay. This is iodine. So it is iodine molecule, then in between van der Waals forces, then another iodine molecules, and so on. So they're linked together, forming a cube. Okay, but this cube is different from just now, where there is one molecule at each surface. On the top surface, there is one molecule in the middle. On the right surface, there's one more. Front surface, left surface, bottom surface, and the back surface. So there are cube shape with one extra molecule on each surface. So that is iodine. And this is graphite. So graphite is giant covalent lattices. So you can see these are the carbon atoms that arrange in a way. What kind of way is that? You can see, let's say this is the carbon that we consider now. So you can see it linked to 1, 2, 3. It linked to 3 carbons, meaning that this carbon, okay, let's say this carbon, it have 3 neighbors, 3 neighbor carbon. Okay, so that is where it is using sp2 hybridizations to form 3 sigma bond. To form 3 sigma bonds. And after that, you may be wondering, carbon has 4 valence electrons, so 3 has been used to form 3 sigma bond, should have 1 more. So 1 electron is delocalized. So that's why graphite, right, can conduct electricity because of the delocalized electron. Each carbon contribute 1 electron to be delocalized. So that's why it can conduct electricity. Okay, so compared to this is diamond. So diamond, if you can see one example, let's say, okay, I take this. So if I look at this, then you can see that these carbons have 4 neighbor carbon. So meaning that it is going through sp3 hybridization to form 4 sigma bonds and no delocalized electron and cannot conduct electricity. Okay, so that's the difference. So there's a difference in graphites and diamond. Although both are made of carbon, but they are really different. This is black color, not nice. This one is shiny color, is nice. This one, although it's not nice, but this one, it works well in conducting electricity. So diamond, although it's nice, but it cannot conduct electricity. Of course, it has other usage. So not to say this is nice and useless, but it is useful in terms of, let's say, for example, it is the hardest thing on the earth. So we can use it to cut, let's say, to penetrate the earth crust, to find petroleum. So we can use diamond. Okay, now let's move on. This is silicon 4 oxide. So as you can see, they label it here, where the blue dot is the silicon atoms, and after that they're linked to oxygen atoms. Okay, so how they're linked, let's see one example. Okay, let's say I take this. Okay, so this silicon atoms, it has 4 neighbor oxygens. Okay, so you can see 4 oxygen linked to it. 1, 2, 3, 4. Okay, so after that, oxygens, let's look at oxygen. Oxygens, let's say I look at this, it has 2 neighbor silicon. Okay, so you can see they are in difference. So I mean, silicon takes 4 oxygen as neighbor, and then oxygen take 2 silicon as neighbor. Okay, so the structures is still tetrahedral shapes actually because of the 4 sigma bond of the silicons. So it's tetrahedral shapes, similar to diamond. Diamond is also tetrahedral shapes, but the thing is it has oxygen in between them. Okay, so tetrahedral. Just now the just now we learned maybe I put it together in this way. So graphite, and then Buckminster fullerene, the C60 just now, and diamond. Okay, so these 3 are made of carbon, so we call these allotrope of carbon. So they are all made of carbon, but they have different structures. Okay, so when I compare this and this, right? So the first one, Buckminster fullerene, you have to know that this is doing sp2 hybridization. This is sp2 also. This one sp3. Okay, so sp2, if you still remember, is trigonal planar, the shape. So, and sp3 is tetrahedral. Okay, so and silicon 4 oxide is also tetrahedral. Yeah, so now we have done covalent lactases. Now we look at metallic lactases. So you can see metals form giant metallic lactases in which the metal ions are surrounded by a sea of delocalized electrons. So for example, sodium positive and A plus. So it's surrounded by electrons which delocalize. Okay. So the metal ions are often packed in hexagonal layers or in a cubic arrangement. Hexagonal or cube. Okay, so let's see the next page. So you can see here layers of copper ions, and the delocalized electrons are not shown in the diagrams. Okay, so basically what happened is it is Cu2 plus, not copper atom, it's copper 2 plus. So it's something like this is Cu2 plus electron, Cu2 plus electrons, Cu2 plus electron, and so on. So look like that. Okay, so the electrons can go anyway, and let's see the exam tips. Yeah, graphite, diamond, and Buckminster fullerenes are allotropes of carbon. This is what I mentioned just now. They are all made of carbon, but it has different structures. So this one ball shape, this one tetrahedral. This is this is ball shaped. This one tetrahedral. This one is like layer by layer. So we have one layer of it's something like this. We have one layer, one layer, and one layer. So that is graphite, layer by layer. So it's layer by layer logically because they are sp2, right, trigonal planar. So they form one flat layer and then another flat layer here and then another flat layer here. So they are held together by van der Waals forces. So there are different structural forms of the same element, which is carbon. So we call these allotropes. Okay, now let's move on. Okay, so we have learned lactases. We have learned ionic, covalent, and metallic lactases. Now let's see the effect of bonding and structures on physical properties. So of course, this bonding is chapter 3. The structure itself is chapter 4. And then we want to see the effect of chapter 3 bonding and Chapter 4 structures on physical properties. So different types of structures and bonding have different effect on the physical properties of substances, such as their melting and boiling points. So for example, diamond has very high melting and boiling point because it has many covalent bonds to break. And electrical conductivity, for example, graphite can conduct electricity because it has delocalized electron. And solubility depends on whether it can form any bonds or intermolecular forces or hydrogen bonds with water. So if they can do that, then they are soluble in water. Okay, so let's see here. Ionic bonding and giant ionic lattice structures. So ionic compounds are strong. The strong electrostatic forces in ionic compounds keep the ions strongly together. So positive and negative are holding. The attraction between positive ion and negative ion is the electrostatic force. So they are attracting and they are hold together because of the attractions. So they are brittle, as ionic crystal can split apart. Brittle, imagine salt. So you can just use a spoon to break a big piece of salt to a small pieces. So that is brittle. And ionic compounds have high melting and boiling points. So the reason is here. The strong electrostatic forces between the ions in the lattice act in all directions and keep them strongly together. Okay, so that's why it has high melting and boiling point, because of the ionic bond. So melting and boiling point increase with charge density of the ions due to the greater electrostatic attraction of charges. Okay, so let's understand this term, charge density. Charge density, okay, what is that? It is actually charge over size. That is charge density. So for example, let's say I talk about sodium, magnesium, and aluminium. So these three stay in period 3, and when we go across period 3, the size decreases. The charge increases. Okay, so now I'm going to ask you, the charge density, when I go across these three, the charge density increase or decrease? What do you think?
Is it increased?
Yes, correct. Charge density, which is equal to charge over size, increase. When this increase, this decrease, mathematically you should be able to imagine. So it is going to increase. Okay, now that means what? That means the ionic bond that form here, so it's going to be stronger and stronger when you go from here to here. So it forms a stronger ionic bond when you go to the right. Okay, so example, magnesium oxide has a higher melting point than sodium chloride because this one has a higher charge density, and hence the ionic bond is stronger. And ionic compounds are soluble in water, as they can form ion dipole bonds. So you just need to check whether they can form any force or attraction with water. So if yes, then it is soluble in water. Okay, so what is ion dipole bond? So of course, ion means, for example, Na plus and Cl minus are ions. Dipole refer to H2O, which has delta positive and delta negative. That is the dipole. So the ion and the dipole attract each other, and because of that, it is soluble. Okay, so ionic compounds only conduct electricity when molten or in solution. So of course, what happened here? Molten means it is melted or it is in liquid form. So if the ionic compound is in liquid form, basically you want to melt it, you need to break its its ionic bonds. And after breaking its ionic bonds, so the ions are free to move around and hence it can conduct electricity. And then likewise in solutions, when the ion dissolve, then the ions are not held by the ionic bonds anymore, they are freely moving around, so it can conduct electricity. So when molten or in solution, the ions can freely move around and conduct electricity. In the solid state, they are in a fixed position and unable to move around. Okay, so these are the physical properties. Okay? What kind of properties you have? You have whether it can conduct electricity, whether it can dissolve in water, or whether it has high melting point and boiling point or not. Okay, so basically these three are the physical properties. Okay, now let's see metallic bonding and giant metallic lattice structures. Okay, we look at their physical properties now. So metal, you should know, metals are malleable. So the meaning of malleable is they can pull into wires. You can pull into wires. So we look at the picture first. This is the metallic lattice. So you can apply force in this particular way. You use machine to pull the upper part to the right, the lower part to the left. Then after that, the two layers slide over each other, and then this one form one piece of wire, and then this one is another piece of wire. So it works in this way, and we call this malleable. Okay, so it can slide over and reform. Okay, now when a force is applied, the metal layers can slide. The attractive force between the metal ion and electrons act in all directions. So when the layers slide, the metallic bonds are reformed. That means when it slide, it break. When it stops sliding, then it reform the metallic bonds. And then, so when the layers slide, the next point, the lattice is not broken and has changed shape. Okay, so you can change the shape. So malleable. Okay, now metallic compounds are strong and hard. Before we continue with this, actually there is another term which is used here, which is called ductile. Have you heard before ductile?
Yeah.
So this is another physical properties of metal. So metals are malleable and ductile. Okay, so malleable means you can pull it into wires. So ductile means you can form shapes. Okay, so now let's move on. Metallic compounds are strong and hard due to the strong attractive forces between the metal ions and delocalized electrons. Okay, so metals have high melting and boiling points, of course, because of the strong metallic bond also. Pure metals are insoluble in water. Okay, metals can conduct electricity when in the solid or liquid state because it has delocalized electrons. So as both in the solid and liquid state, there are mobile electrons which can freely move around and conduct electricity. Okay, so let's move on. Now it's come to covalent. So let's see covalent bonding and simple covalent lattice structures. So giant covalent will come later. So we start with simple covalent first. Simple covalent lattices have low melting and boiling points, basically because of the weak van der Waals forces. So these compounds have weak intermolecular forces between the molecules. Only little energy is required to break the lattice. Most compounds are insoluble with water unless they are polar, such as HCl, or can form hydrogen bonds such as NH3. So you can see to make a molecule to be water soluble, the condition is polar or can form hydrogen bonds. So polar means it has delta positive and delta negative, or the slight charge, or they can form hydrogen bonds, then it is soluble. So they do not conduct electricity in the solid or liquid state as there are no charged particles. So they are just molecules, so they are not ions, so there are no charge. Okay, so some simple covalent compounds to conduct electricity in solution. Okay. A bit weird the sentence. In solutions such as HCl, which form H plus and chloride ions. Okay, so that means HCl can conduct electricity in solution. As we know, HCl is a simple molecule, but when it dissolves in water, it becomes ions, and hence it can conduct electricity. Okay, so it seems like it is having the ionic properties. Okay, so but it is covalent molecule. Okay, now let's move on. Covalent bonding and giant covalent lattice structures. So giant covalent lattices have melting and boiling. Okay, so have high melting and boiling points. So one word is missing. So that's why a bit weird. Okay, have high melting and boiling points. So how high is that? It can come to 4 digits. 4 digits, like 3000 degrees Celsius for diamond and graphite. So, yeah. And these compounds have a large number of covalent bonds linking the whole structures. Intermolecular forces between the molecules linking the whole structure. The sentence is a bit weird here. Okay, so what are they trying to say is actually, for example, diamonds, the carbon atoms are whole by covalent bonds alone. Covalent bond. You want to melt it, you want to boil it, you need to break the covalent bond. Okay, so a lot of energy is required to break the covalent bond. So that's why it has high melting and boiling point. So high. Okay, now let's see the next one. The compounds can be hard or soft. Like diamond is hard, but graphite is soft. Graphite is soft as the forces between the carbon layers are weak. Just now I mentioned graphite is one layer and another layer which are held together by weak van der Waals forces. Okay. Then you can easily cut graphite in this way, and then after that it becomes 2 layers. That's why we call it soft. Okay, so Graphite is soft as the forces between the carbon layers are weak, which is these forces, the one in dotted lines. And then diamonds and silicons for oxides are hard. So imagine diamond, this is sand, sand is hard also. As it is difficult to break their 3D network of strong covalent bonds. You know, they are tetrahedral in shapes. So they are linked together by covalent bonds. You need to break that, it is hard. So that's why they are very hard. Okay, so most compounds are insoluble with water. Logically true, you know. Sand insoluble in water, diamond insoluble in water, or else if you are wearing diamond, you take bath then no more already. So likewise, graphite we use it in electrochemistry or electrolytic cell. So we put the two graphite rod in water or in solution, or they don't dissolve in water. So we should experience that. Now let's see. Most compounds do not conduct electricity. However, some do. For example, graphite, yes. So graphite has delocalized electrons between the carbon layers, which can move along the layers when a voltage is applied. So one layer, this is another layer, so the delocalized electrons are in between. So diamond and silicon 4 oxide do not conduct electricity, as all 4 outer electrons on every carbon atom is involved in a covalent bond, so there are no free electrons available. Okay, so you know, diamond and silicon, they are actually group 14. I mean, diamond means carbon. Carbon and silicon, they are group 14. So they have 4 valence electrons, and they use 4 of the valence electrons to form 4 sigma bond and no more free electrons. Okay, so almost finished already. Now let's see this part. So this is like the summary of all the characteristics. So let's take a look. Melting and boiling points. Okay, so we have giant ionic, which is high because of ionic bonds. Giant metallic, moderately high to high because of metallic bond. Simple covalent, low because of weak van der Waals forces. Giant covalent, very high because of covalent bonds. Electrical conductivity when molten or in solutions. Giant metallic when solid or liquid. Okay, so solid, liquid, that means it can conduct electricity in all situations. Okay, and do not conduct electricity. This one cannot, because no free ions. Do not conduct electricity except for graphite. And we look at solubility. Ionic soluble, metal insoluble, but some may react. For example, sodium. Sodium can react with water. At the end it dissolves. Usually insoluble unless they are polar. For example, HCl, yes. Oxygen also dissolves partially in water. That's why the fish can get oxygens. And giant covalent, no, insoluble. Hardness, hard, brittle. So it is hard, but it can be easily break down into small pieces. Okay, so hard, malleable. Then this is soft. This one very hard. Diamond and silicon 4 oxide, or soft, which is graphite. Okay, so physical states at room temperature. So this is solid, liquid or gas, and this is solid. And you see the forces. Electrostatic attraction between ions, this is ionic bond. The locality of electrons attracting positive ions, this is how the metallic bond works. This is the key concept of metallic bonds. And weak intermolecular forces between molecules and covalent bonds within the molecules. This one we discussed yesterday. So this one is the concept that we learned in chapter 3. Electrons in covalent bonds between atoms. Okay, so covalent bonds basically. Particles, ions. This is positive ion in the sea of electrons. This one is positive ion and negative ion. This is positive ion and electron. So it's different between these two. This is small molecule, this one atoms, carbon atom for example. Okay, so example NaCl, graphite. Wait, hold on. Graphite silicon oxide. Oops, this is definitely a problem. As you can see, this is giant metallic. Here. I mean, graphite silicon oxide should be there. Okay, this one should be here. And Br2 bromine molecule should be here. Copper should be here. Okay, they are playing us around. Okay, so let's move on. Okay, so we have to go through this. So we just discuss straight away. So first we'll look at this table. We have X, melting point, good, solubility in water, soluble. So Y 95, very poor, almost insoluble. Z 1389, 4 digit, good, insoluble. Okay. Which one of the following statement about X and Y is completely true? Okay, so you think about it, then you let me know.
Okay.
Yeah. Okay, so you said number 4. X has a giant ionic structure. Okay, let's see. Melting point, electrical conductivity.
Actually, wait, maybe it's 3.
3. Okay, now you change your mind to 3. X is a metal.
Sure.
Okay, so let's see whether this is metal or not. Metal is not soluble in water. So we have to reject number 3 because metal is not soluble in water. Okay, so I reject 3 first. Then I should reject 2, right? Because X is not a metal. Okay, so then you have to accept X as a giant ionic structure. As you can see, only 1 and 4 remain, right? So X is a giant ionic structure. And how about Y? Is it giant molecule or simple molecule for Y?
I thought it was simple because the melting point is very low, but I'm not too sure.
Yes, so it is correct. It is a simple molecule because it is having a low melting point, and it's a simple covalent. Simple covalent normally insoluble. Okay, so this is correct. Z is a metal. Okay, yeah, true. Because metal normally it has melting point of 4 digits, electrical conductivity when molten, good. Actually, it can conduct electricity in solid as well as liquid. So no matter molten or solid, it is just good. Soluble in water, insoluble. So metal is insoluble in water. So at the end, we have to say that the answer is number 4. Number 4. So that's why when you do multiple choice, sometimes we have to reject first before we get the answer. So we reject 2 and 3. Then only 2 choices remain. Then we just look at why to decide. It will be easier. So we reject the wrong one first. Then we choose the answer afterwards. Okay. So